You can continue, please. Sorry.
Okay, thank you. Thank you for the organizers for such a great opportunity to be here to talk about this work. The title of my talk is Partial Symmetrical Product of Multiplier Hopf Algebras. This is a joint work with Martini and Fonseca. And when we, in this line of research, when we are dealing with multiplier Hopf algebras, actions and coactions, our goal is to extend this theory to a partial setting. One of the main references that we have for this kind of work are the papers produced by Van Dale, who introduced in 1994 the multiplier Hopf theory in the algebraic context. And there are a lot of works written by Van Dale in this setting, dealing with actions, coactions, representations, co-representations, Morita-Galois theory, and so on. Although the original definition have been given by Van Dale, in this talk I would introduce an alternative definition given by Timmerman. Before this, throughout this talk, I'm going to fix a field K. So over the vector spaces and over the algebras will be considered over this field. As I said, the definition given by Timmerman, the definition of multiplier by algebra, then he considered a pair with an undegenerate algebra and an undegenerate homomorphism that these two conditions hold. Here we have a multiplier algebra of the tensor product. We are not dealing with unital algebras, but in this algebra we have unity, and these four products are contained in the tensor product. And the second condition, we have generalized as co-associativity. Here important notice that the image of this map lies in a larger algebra. So this second condition is an extension. So it is possible because we have an undegenerate homomorphism here. So all the time that we have this assumption, we can extend the maps that we are dealing. And if you have these linear maps bijective, then we have multiplier Hopf algebras, a multiplier Hopf algebra. An important result that we have in this theory given by Van Dale is about the existence of local unities. And is important result because it allows us to use the Swiller's notation in this context. So we have a multiplier Hopf algebra. For any finite set of elements, exists this element that is a local unity. It means that this equality holds. And so at the first, we have this product in the multiplier algebra. This unity that appear here is the unity in the multiplier algebra. So here we have a product in this algebra, and this last equality is the way that we write this expression. Of course, here we have some kind of dependence of the element, but for finite elements, you can choose the same. The first example that was given by Van Dale, constructed by Van Dale, is the algebra of finitely supported complex functions on a group. And here we consider it easy to prove that the multiplier algebra of this algebra consists of all complex functions on the group G. But here we have some identifications for show that we have this coproduct defining a coproduct in the sense of Timmerman. So we have some isomorphisms here to show that. But here is also possible to show that we have co-unity and antipode. So we have a multiplier Hopf algebra, one of the first examples that we have in this theory. As I said, our goal is to extend the theory to a partial context in the sense that it generalizes the Hopf structures in also the global ones. So here we have the definition given by Batista and Joost of partial commodial coalgebra, and we have the three conditions. The last condition is related to symmetric condition. Here is a definition, is a known definition in the Hopf contest, in the partial Hopf contest. And our definition in this context, we have to consider two regular multiplier Hopf algebras. The condition of regularity here, it means that if we have a pair that is a multiplier Hopf algebra, then the composite map with the twist with the coproduct also is a multiplier Hopf algebra. And we define a partial A comodual coalgebra if there exists this linear map. Here we have again a larger algebra. So the most of these conditions that are imposed here are extensions. The first one, we have the image of this map in the multiplier algebra. So here we have a non-degenerate homomorphism, then we can extend. And the second condition is important because in the third condition, we have to define another extension is common in this the two in this theory. Defining extensions and then prove that we have some multiplier in some space, and then we can rewrite these expressions in a way that we can to make some calculations. And the second condition is important to make sense for the conditions 3 and 4. The T-map that appears here is defined like that. This idea is based in the definition of global comodual coalgebra that has given by Lydia Dalvaux. And here we have this expression in the tensor product. So here we are able to use the sigma notation because we have an expression in the tensor product. We like a lot of dealing with symmetrical conditions. So here we have the similar conditions for the symmetry. Here also appears analogous of this map T, this T map. Here we have a T bar. Again, here we have a possibility to use the sigma notation. And this definition also extend the definition in the global context of Lydia, and also extend the theory of the constructed by Eliezer and Joost in the Hopf context. Here we have a result that is a family of examples. So we define a linear map. Here taking an element in the multiplier algebra of the algebra A. And we have this kind of equivalence. We have a symmetric partial A comodual coalgebra if and only if these three conditions hold. Again, the third condition is related to symmetric condition. This example here, we are using the definition given by Timmerman about integral and co-integral. Here we fix this element in algebra. There is a co-integral in this case that satisfies this condition. Then we define this linear map, and then we are able to prove that we have another symmetric partial A comodual coalgebra. Here we are just specifying the previous example here using the driving example given by Van Dale. But here we are defining this map. This map lies in this algebra AG, and we have a specific example by the previous, given by the previous. Here we have some kind of a mix of Hopf algebras and multiplier Hopf algebra. We consider a Swiller Hopf algebra, and we define this linear map. Consider the prev H element in the algebra AG, and this element in the Swiller Hopf algebra. Then we prove that we have another partial comodular coalgebra. Here another example, but in this case using the Taft. Again, we take some element in the algebra, in the Taft algebra, and we consider the preview of the same element in the algebra AG, and we have another example. Here we have another way to construct examples in this theory that using projections. This idea also appears in the Hopf context when we take some global structure, then we project to a subalgebra, and in the subalgebra we induce some partial structure. But we are not dealing with unities here, so we use the idea of projections that are the same in some sense. But here we consider a regular multiplier Hopf algebra and a regular multiplier subalgebra. And here we define a projection. We consider a projection, and we take the definition in this context of commultiplicativity. Here I am explaining what does it mean, because again, the image of this map lies in the larger algebra, in the multiplier algebra. Then we have to explain what does it mean, this composition. So these two expressions explain what does it mean to make this composition of pi and delta in this context. Of course, we have to ask some conditions for this projection. And here we consider a comodular coalgebra, global comodular coalgebra, and a regular multiplier Hopf subalgebra. In a projection, then if we have these three conditions for the T map and the commultiplicativity, then we have a partial comodular coalgebra using the global one. So we are projecting using the structure that we have in the global. We say that is an induced partial comodular coalgebra. Here we have an example, just in a specific example using the idea of projection. It's not so easy to construct projections that satisfy all the properties, but here we have an example considering a group and a subgroup with an idempotent element. Then we consider the group algebra, and we can construct this linear map. And we have a specific example of induced partial AG comodular coalgebra in this context. Our goals is construct the coproduct, this mesh coproduct in this context. So using the ideas by Lydia in the global, we define these two maps. Here, again, we have to think these expressions like extensions. But the first one, if we look to definition, these three terms that we have, here is a composition of operators, but this expression lies in the tensor product. In this second one, we can define a multiplier, but these two expressions lies in the tensor. And we use these two maps to define the coproduct in this context. So we consider a partial equimodular coalgebra, then we define this multiplier. We are dealing with multipliers, so all the time we have to define a left and the right side, and then prove that some compatibility hold. And here we are able to prove that this, in fact, is co-associative. Here, this remark is just to show that in some cases it's easy to rewrite this expression in the sigma notation, but in another it's not so easy. But we can prove that we have this expression in the tensor. The first one here, we have to define an operator, prove that we have a multiplier, and then we can rewrite this expression in a sigma notation. But the second one, it's not possible, but by the definition, this expression below lies in the tensor. So the next step, we have to prove that we have the delta bar has a multiplicative map. So we define comodular B-algebra in this context. This definition also appears in the global, and the definition is that we have the both structures. We already have the comodular coalgebra defined, and the definition of partial comodular algebra. It is defined in our previous paper that I didn't mention it here, but it was defined. So if we have the both structures of comodular coalgebra that I defined in this talk, and the partial comodular algebra, then we have a comodular bi-algebra. And if we have the symmetry condition, we call a symmetric partial ecomodular bi-algebra. Then we have this theorem. Then we have, if we have a symmetric partial ecomodular bi-algebra, such that we have the algebra commutative. This also appears in the global ones. So here we have to impose this condition also. Then we have the proof that we have the tensor has a multiplier by algebra in the sense of Timmerman. So we prove that we have a coproduct that is a multiplicative structure. And we denote this multiplier by algebra like this. The next step would be to prove that we have co-unity. And we define this in the usual way. But we also able to prove that we have left co-unity. This problem also appears in the Hopf contest. We are not able to prove that we have left right co-unity in this context, but we have some restrictions to in algebra. Here we are doing in the general context. We define in the general, then we just replace our case for this. So we consider this a general multiplier by algebra with left co-unity, defined like this. In fact, this we think like a multiplier, but here we see just like an elements. But in fact, it makes sense like a multiplier. Then we prove that we have a multiplier sub-algebra. Then, and we have that proof that we have co-unity, right co-unity, because we already have left co-unity here. So, taking our case, using the previous result. We have an X structure of co-unitary multiplier by algebra here that we call partial special product. And here, this result is important because we have some concrete way to rewrite this construction. Firstly, we consider a symmetric partial equal module by algebra, defined like this. Considering this hypothesis for this element H in the multiplier algebra and the algebraic commutative, then we prove that we have this subalgebra has a multipliers Hopf subalgebra, and we have this concrete way to rewrite the construction. And we prove that showing that the structures are the same, even in this coproduct, even this. And here we take the driving example constructed by Van Dale. Consider a symmetric partial comodule coalgebra defined like this. Then we prove that this map have a structure of comodule algebra, partial comodule algebra. Then we have a partial comodule by algebra. And using the previous result, we have this isomorphism, this identification, concrete identification. And here, like we are considering this specific function that are defined and using the subgroup of a group G, we have more specific here than we have this isomorphism, has co-unitary multiplier by algebra. This is the way that we are dealing with the functions, because the product in the multiplier algebra AG is a punctual product. So we have this expression that make the calculations more easier. And I think it is. Here we have some references. Thank you so much. Thank you for your patience.